Up until now, we've pretty much looked only at pairs of electrons. We've seen pairs of electrons being transferred, especially when we draw our arrow pushing diagrams. In this chapter, we're going to start looking at radicals, which have unpaired electrons, which opens up a whole host of new reactions that we can use. So, the key thing to see here is that instead of having our double barbed arrows that we typically show for a movement of two electrons, we're going to use what are called fishhook arrows or single barbed arrows. These represent one electron being moved. We've seen these fishhook arrows before when we talked about bonds breaking homolytically versus heterolytically. Okay, so one of the steps that we're going to see that where radicals are formed in this chapter involve the homolytic cleavage of bonds, of covalent bonds, where the two electrons are split up and you form two radicals, each with one unpaired electron. So, what do free radicals look like? Well, we've already seen carbocations and carbanions, right? With a carbocation, we have an sp2 hybridized carbon with an MTP orbital. In the case of a carbanion, that carbon is sp3 hybridized with one of those orbitals filled up with just a lone pair. It's not got a covalent bond to anything. Okay, and that's what houses that negative charge. A radical is kind of like a hybrid of the two. Okay, so you could think of it as your sort of like a carbocation, so it's sp2 hybridized, trigonal planar, but there's an electron in that quote-unquote MTP orbital, so I guess it's technically not empty anymore. You could also think of that electron with its electron density kind of pushing down on the bonds and forming a sort of sp3 hybridized carbon as well. So it's kind of like a carbanion, but just missing one of those electrons in that p orbital. Okay, so instead of getting a complete trigonal pyramid shape like you typically see in a carbanion, we have a sort of shallow pyramid, which allows for a rapid intraconversion between the sides on which that unpaired electron is found. Okay, so which makes for some interesting geometry involved there. So unlike a carbanion, which has a set geometry, your radical is kind of like a carbocation, where it can be kind of attacked from either side. All right, so we've seen with carbocations that we have a difference in stability as we add more and more alkyl groups to that carbocation. We see the same thing here with radicals. So generally speaking, radicals get more and more stable as you add more alkyl groups. So a tertiary radical is more stable than a secondary, which is more stable than a primary, which is more stable than a methyl radical. Okay. All right. So because of this, if we looked at the bond dissociation energy for a carbon-hydrogen bond, we can see that that dissociation energy decreases as we add more alkyl groups to our alpha carbon, because, well, consider the resulting radical that would form when you break that carbon-hydrogen bond. Okay, so the more stable the radical you form, the less energy it costs to break that carbon-hydrogen bond. So that's a good way to sort of measure the stability of a resulting radical by seeing how much energy it costs to pluck off that electron. That hydrogen. Okay, so another thing to consider when it comes to radicals is that we have allelic stability. So we've seen this with carbocations and carbanions, where if you have an allelic, you have your charge in the allelic position, that's one bond away from a double bond, you have a resonance stabilization there. Okay, so we see the same thing with a radical at the allelic position. We can have some resonance stabilization there. Of course, now how we show that resonance is going to be a little bit different. We're going to use our fishhook arrows here as opposed to our regular arrows. So for example, if we had a carbocation, okay, or I guess maybe it might be easier to show this with a carbanion. Okay, so let's say we had a lone pair here and a negative charge. okay, we could have those electrons swing over here, and then these electrons swing over here, and we get that resonance structure that looks like this. There's an extra lone pair in this carbon, and we have a negative charge. Okay, I've left off all, the hydrogens obviously on that are here. This is just a skeletal structure. But basically, this is what that resonance looks like for a carbanion, and of course, something very similar for a carbocation. In the case of a radical, since we only have one electron moving at a time, what happens is this electron moves to this bond here to form half of the pi bond that we're going to form, whereas this pi bond cleaves and sends one electron to complete that pi bond that we form, as you can see here, and the other one moves over here to form this radical on this side. Okay, so it's very similar to kind of the electron movement we see for a carbanion or carbocation, but obviously, the way we move these electrons is a little bit different. Okay, so if you want to see the hybrid structure for that, again, you've got a little bit of radical character on each of those terminal carbons, and of course partial double bond character on both of those covalent bonds. Just like with the allelic position, we've seen that the benzylic position is very stable for resonance structures with carbocations and carbanions, and of course with radicals we have the same process. So here you can see that if we just look at this chunk over here, this is essentially the same allelic system that we saw on the previous slide. So the only difference now is that this is just sort of spread out throughout the whole benzene ring. Okay, so you can draw more contributors that look like this, and of course you can get a hybrid where that double bond character is spread throughout the whole molecule, as well as that radical. And so again, that increases the stability through resonance. Okay, so you can see this again with bond dissociation energies. You can see that here we have a tertiary radical on the left, and for an allelic radical forming and a benzylic radical forming, you can see that the bond dissociation energies are even lower because of the stability of those resulting allelic and benzylic radicals. So clearly resonance is more important than hyperconjugation when it comes to stabilizing a radical. Okay, just as we've seen that the vinylic position is unstable when forming carbocations or carbanions, especially in contrast with allelic positions. Again, same thing here. The vinylic position is not going to be suitable for forming a radical either. Just in the same way as with carbocations and carbanions, you can see that the bond dissociation energy for our vinylic hydrogen is much higher compared to even a primary radical forming. Okay, now that being said, there are key differences between radicals and carbocations, and I think probably the main key difference here is the ability to rearrange. We've seen that carbocations will rearrange to make more stable carbocations through either a hydride shift or a methyl shift. For example, this carbocation here is a secondary carbocation. One of the methyl groups to the left of it will shift over and form a tertiary carbocation over here. So basically, this methyl group would move over here, and this carbon over here would get a positive charge instead, and this would be a tertiary carbocation. We do not see an equivalent shift in our secondary radical over here. This will remain a secondary radical. It will not form a tertiary radical, even though a tertiary radical would be more stable. Okay, now, that being said, since our rearrangements was one of the four key steps we saw in various mechanisms, in all of our arrow pushing mechanisms, and then we got into the habit of paying attention to that and recognizing those patterns in all of the mechanisms we see, I want you guys to do something similar here in this chapter with radicals, except instead of 4, there are 6 key arrow pushing patterns that you need to recognize. Now, don't panic. You'll see that just like with a leaving group leaving and a nucleophile attacking, just like those two patterns are kind of reverses of each other, we also have these sort of couplings of these patterns in our radical arrow pushing patterns. So let's go through those. So the first one we've got is homolytic cleavage, and that's something we've seen before. It's where a bond breaks and each of the two electrons in your covalent bond, one goes to each atom that was involved in that bond, and you get two radicals. All right. Now, what usually gets this going is energy provided either in the form of heat or light. Okay, so typically you'll see the Greek letter delta representing heat, or h nu, okay, that's Planck's constant and frequency, together representing energy from light. Either of those will be written on top of your arrow, okay, to show that that's what's, pushing that reaction forward, what's initiating that reaction. You can have an addition to a pi bond, where you have a radical coming in, and it reacts with an alkene. And what happens is the pi bond in your alkene opens up, and it forms a covalent bond with the radical, and this causes the other carbon that was part of your pi bond to instead pick up the radical. Okay. So again, this is the arrow pushing pattern you see here. Out of the two electrons in your pi bond, one forms the covalent bond with the radical in the atom coming in. The other electron from that pi bond forms the new radical. Over here we have a hydrogen abstraction. This is where a radical comes in and plucks off a hydrogen from something with a hydrogen. Okay. Please note this is not the same as a proton transfer, though it is very similar. The key difference here, of course, is that we're using fishhook arrows and not, we're not doing a heterolytic movement of arrows of electrons. So in a proton transfer, you have your base coming in and it donates 2 electrons to that hydrogen, and then both the electrons of that bond would go to your conjugate base from that hydrogen, right? To the acid, the rest of the acid, I guess. In this case, the unpaired electron from your radical forms half of the bond. This covalent bond homolytically cleaves, where one electron forms the rest of that bond to hydrogen. Okay, so these two, that one electron from here and one electron from here, form this bond over here with a hydrogen. And the other electron from this covalent bond turns the rest of that molecule into a radical. Okay. Similarly, we can do a halogen abstraction. It works in the same principle. The only difference here is that we're starting off with, instead of transferring over a hydrogen, we're transferring over a halogen. Okay, that's what X is. So this molecule here could be a chlorine or a bromine or whatever. And we'll see, the factors that go into that. Usually it's a chlorine or bromine. Okay, we'll see why it's not fluorine or iodine later on. But basically, that's essentially what we're doing. So here your molecule's picking up a halogen, and that's why it's a halogen abstraction. Okay, so please note the difference between these two. The similarities and the differences. You can see the similarities in the arrow pushing. The difference, of course, is look at what your radical's picking up. Okay, the radical here is picking up a hydrogen. The radical here is picking up a halogen. We can also do eliminations. Now, notice that the elimination step is going to be the reverse of the addition to a pi bond. Again, this is one of those couplings I kind of told you about. Okay, so basically it's just as in the addition to a pi bond, you start off with a radical and it would react with a pi bond to sort of form a covalent bond between that atom and your carbon and turn the other carbon into a radical. Here the reverse process happens. This radical forms half of your pi bond. This bond is going to homolytically cleave one electron will form the other half of that pi bond, and the other electron will go and turn that atom into your leaving group. Now, please note, this I was about to call this a leaving group because it seems like that. Technically, it's not a leaving group for the same reason why a hydrogen abstraction is not a proton transfer. This is not taking both electrons heterolytically from that bond. It's only taking one electron homolytically. Okay, And that's the key difference there. That's why it's not a leaving group. Okay, but the same concept applies, where it's you're breaking that covalent bond, and this group is taking an electron with it. Okay, it's just not taking both electrons with it. Okay, and then we have finally a coupling reaction, where we have two radicals that come together and form a covalent bond, and it's just the reverse of a homolytic cleavage. Okay, you'll see that this is often the termination step of some of the mechanisms we're going to look at. All right, so unlike our regular double barbed arrows, where a lot of the mechanistic steps involved just one arrow moving, or at most two arrows moving, here we're going to have 2 or 3 fish hooks moving around. Okay, so you're never going to find just one fish hook typically in these mechanistic steps. All right, so watch out for that. All right, so as I pointed out, in terms of trying to remember these patterns, or to memorize them, it does help to notice the similarities or see how they're kind of coupled together in pairs. Okay, so remember that homolytic cleavage and coupling are just the reverses of each other. The addition to a pi bond and elimination are also reverses of each other. And hydrogen abstraction and halogen abstraction are both kind of similar. Okay, here are 2 hydrogen abstractions being shown, but the concept is very similar. Just think about what your radical is picking up. In this case, your radical is picking up a hydrogen in both these steps, right? Here, your R radical picks up the H to do this reverse reaction, to pick up that hydrogen here. In the forward reaction, your X radical is picking up the hydrogen to form this. Okay, in a halogen abstraction, it's the same thing, except your radical's picking up a halogen. Okay, now how do all these steps come together to form a full mechanism? There are 3 phases, right? We have an initiation phase, a termination phase, and a propagation phase. Okay, that's kind of the middle of this reaction of the mechanism. All right, so the initiation step is where radicals are created. The termination step is where the radicals are destroyed, and that ends the reaction. Okay, the propagation step involves the just essentially you start off with a radical and you end with a radical. Okay, so out of the 6 mechanistic steps we learned, your initiation step is pretty much always a homolytic cleavage. That's where radicals are generated. Your termination step is pretty much always a coupling, where radicals are destroyed. And your propagation step is some combination of the other 4 steps. Okay, when I say some combination, it doesn't mean you have to have all 4 steps, but those other 4 types of mechanistic patterns are found in the propagation phase of your mechanism. Okay, so you're going to see addition to pi bonds, see hydrogen abstractions, halogen abstractions, eliminations. Okay, so let's see an example. Let's look at the chlorination of methane. Okay, so here we're taking methane, which is an alkane, and we're going to add chlorine to it. Okay, we're going to see later on, like, this is very, very useful. Okay, alkanes in general, are pretty unreactive. So this is a great way to introduce a functional group to something that's otherwise pretty unreactive. So to do this reaction, we're going to take our alkane, our methane, and react it with chlorine and shine light on it. Okay, so that's represented with the H nu underneath the arrow there. Right? So in one turn of this reaction, we swap out a hydrogen for a chlorine. So our products are chloromethane, or methyl chloride if you want to use the common name, and hydrogen chloride. Okay, so let's look at the full mechanism for this reaction. So we start off with our initiation step, where the chlorine molecule homolytically cleaves into 2 chlorine radicals. Okay, so this is where the light comes in. Shining light on the chlorine helps encourage this cleavage. Okay, to answer that question down there, is homolytic cleavage also likely for methane? I want you to think about the bond dissociation energies involved here. Is a chlorine-chlorine bond more likely to break than a carbon-hydrogen bond? And the answer is yes, right? Chlorine two chlorine atoms are relatively large, so this covalent bond between the two chlorines is a pretty long, weak bond, and so it's relatively easy to homolytically cleave. It probably has a relatively low bond dissociation energy. Okay, it doesn't cost that much energy to break this bond. Okay, whereas a carbon-hydrogen bond generally takes a lot of energy to break. Okay, so now that was our initiation step. Let's see what those chlorine radicals do in the propagation step. So our first thing we're going to see is a hydrogen abstraction. Our chlorine radical reacts with our other reactant, the methane, and it plucks a hydrogen off of it. When it does that, it forms HCl, which is one of our products, and it forms a methyl radical. Now, this methyl radical is going to be involved in the next propagation step. This methyl radical is going to react with a chlorine molecule and do a halogen abstraction. So it plucks off a chlorine from that. And now here you can see we formed our chloromethane, which is our other product. And we have a chlorine radical again. Okay, that's the other thing that's left over from this halogen abstraction step. Well, now notice that this chlorine radical you've produced is the same as this chlorine radical here. Okay, it's not literally the same, they came from different molecules, but my point here is that now you've essentially set up a chain reaction. This chlorine radical can then find another methane molecule and repeat this whole process over and over and over again. Again, that's why this is the propagation step. This is how you generate your products, but you essentially do it kind of catalytically. Finally, we come to the termination step, where two radicals have to couple together and become a molecule that, that's neutral and therefore unreactive. It's just a product. Okay, so what are the products we get in the termination step? Okay, obviously we get the bulk of our product from the propagation step. I pointed that out earlier, right? In each step of the propagation, we get one of each of our two reactants. Okay. But look at the termination possibilities here. What radicals did we have floating around in our propagation step? Well, we have chlorine radicals, we had methyl radicals, and, well, that was about it. So, what combinations can we have? Well, we could have a chlorine radical reacting with a chlorine radical, we could have a methyl radical reacting with another methyl radical, or we could have a methyl radical reacting with a chlorine radical. Okay, so all three of these are possibilities for a coupling. So the first one produces a chlorine molecule, which is one of our reactants. So this chlorine molecule could go on then to, react again. Over here, we form chloromethane, which is one of our products. Okay, so that's our product, and again, that'll add to our products. Our last possible product here is actually an ethane molecule. Okay, so we will get a tiny quantity of ethane as a byproduct of this reaction. Okay, now that being said, keep in mind there aren't a lot of these methyl radicals floating around. So, basically this is only going to be a very, very minor product. Okay, so the odds of two methyl radicals reacting, running into each other to form this product is very unlikely. Okay, there's going to be much more of an excess of chlorine, so it's more likely a methyl radical is going to run into a chlorine radical and form this product that we're trying to make. Okay, so I pointed out earlier that your propagation steps are kind of a chain reaction. So if we cross out our intermediates, right? So notice that our chlorine radical is used up here, but it gets regenerated over here. Likewise, we have our methyl radical, and that's an intermediate because it's produced here and used up here. Okay, so technically, I guess the chlorine radical behaves catalytically. Right? It's used up in one step, but it's regenerated in a later step. Okay, that's kind of what a catalyst does. Okay, over here our methyl radical is an intermediate. It's produced in one step, but it's used up in the subsequent step, so you don't see it in the final product. All right. So the bottom line here, though, is they cancel out, and if we add up the two propagation steps, notice that we get the net reaction, where methane reacts with chlorine, produce methyl chloride and hydrogen chloride. Okay, so yeah, that's basically how this reaction works. So just to recap, you start off with the initiation step, which produces chlorine radicals. Okay, depending on how much chlorine you've got, you probably could have a lot of these radicals. But that being said, since it behaves catalytically, you technically don't need a lot of it. Okay, Then we get the propagation step. In the propagation step, we first do a hydrogen abstraction, which forms one of our products, HCl, and our methyl radical goes on to the next step, where we do a halogen abstraction. Okay, our methyl radical reacts with chlorine to form our other product. Okay, and of course it regenerates the chlorine radical to repeat step 2 again. Right, and then of course the termination steps end the reaction. All right, so I pointed out earlier that these are chain reactions because you're regenerating the chloride radical. These 2 steps in your propagation can just keep on happening over and over and over again. All right. Now the problem with this, of course, is that it's hard to limit your product to just your methyl chloride. Then, because of this propagation, it's possible that you could get a chlorine radical abstracting a hydrogen from your methyl chloride product, and you then get methylene chloride or dichloromethane. You could then get chloroform, okay, or trichloromethane. And finally, you would wind up with carbon tetrachloride. Okay, at this point you have no more hydrogens to abstract. Okay, so if you have a lot of chlorine present, that's one downside to having a lot of chlorine present. That kind of pushes this distribution of products to having more and more chlorine substituents. Okay, so that's something to watch out for. So we have to keep that in mind when we're trying to control this process. Okay. All right. So that being said, here is an example of of an alkane reacting with chlorine. All right. So again, we're doing we're doing a chlorination here, and here are some of the different products we could make. Okay. So ask yourself, which of these are probably major products? Which one's a minor? Okay, so here's how each of those are produced, right? So the main product we're making here is a hydrogen abstraction from the central carbon. Now, please note that the radical we're making here is a tertiary radical. So that it makes sense that this will yield our major product, right? Okay. Of course, now if this then has only hydrogens present at the at your peripheral carbons, you then get a dichloro product that looks like this. So this is also another major product that forms. Okay, and of course you can keep on plucking away, hydrogens from other carbons. Okay, but depending on how many, how much chlorine you've got, you might limit how much polychlorination you might get. Now, this is a minor product where you have a chlorine swapping out for a hydrogen on one of your peripheral carbons, but not that central one. Okay, that seems kind of unlikely because this radical is less stable than that tertiary radical over here. Okay, so it's kind of unlikely you form this without first forming this major product. Okay, so yeah, so that's a minor product that we would form. And likewise, you probably have very few of these radicals floating around. Well, definitely very few of this radical, right? And you need these 2 radicals to couple together to form this product. So this is going to have a very low percentage. Okay, the odds of these 2 radicals meeting to make this product is very, very low. Now, in this example, we use chlorine as our initiator. Our initiation step involved homolytically cleaving chlorine to get chlorine radicals, and that was great because we needed chlorine radicals anyway for our propagation step. However, there are better choices for initiators where you can form them more easily, more readily with less energy. For example, if you use a peroxide, you can see that the energy required to break that oxygen bond is almost 100 kilojoules lower than that for that chlorine-chlorine bond. Okay. Likewise, in the case of the very, the resonance stabilized radical we form with an acyl peroxide cleaving, that's an even lower bond dissociation energy we need. Okay, so the idea here is that you have lots of options for your initiation step. All right, so you don't necessarily have to use chlorine as your initiator. You could use a peroxide or an acyl peroxide and then have that react with chlorine to produce the chlorine radicals you need for the propagation step. All right. So to look at this backwards, while initiators produce radicals that will get radical reactions happening, sometimes we want to stop radicals from reacting. Okay, and that's where radical inhibitors come in. Sometimes we want to avoid that chain reaction process, or stop it, or just prevent it happening in the first place. Okay, basically, um, oxygen is a good example of something that can form a radical really quickly, because you have a double bond. You have a pi bond between the two oxygens, which can homolytically cleave and turn your oxygen molecule into a diradical. Well, this diradical can then go on and quickly react with other radicals. Okay, so an even better inhibitor would be an example of hydroquinone. Okay, with hydroquinone, you can see here by doing a hydrogen abstraction with a radical, it has two hydrogens available here. So you have it reacting with a radical, the radical does a hydrogen abstraction. Well, the resulting oxygen radical that you make is resonance stabilized, okay, and if you have it react with another equivalent of radical, it does another hydrogen abstraction, now you've got an oxygen diradical, right? Well, that quickly undergoes resonance and forms benzoquinone, which is a very stable hyperconjugate, or a very stable system with conjugate pi bonds, right? So yeah, that basically helps it sort of soak up free radicals that are floating around. Okay, now we used a halogenation reaction as an example of a radical reaction. And again, it's a very typical reaction, and I pointed out back then it's very useful, right? Alkanes aren't very reactive. Doing a halogenation is a great way to introduce a functional group to these molecules. Let's look in a little bit more detail the difference between the different halogens. And let's look at the thermodynamics involved in this reaction in general and understand why this influences our choice of halogens for carrying out this reaction. Okay, so first let's look at our Gibbs free energy equation, right? So remember, we have an enthalpy term and an entropy term in that equation. Ideally, we'd like delta G to be negative for the reaction to be spontaneous. So we need the enthalpy term, or basically, if ideally you'd like both your enthalpy term and entropy term to wind up overall being negative. But if one of them isn't, you have to hope that it's smaller than the other to avoid, to sort of cancel out. Okay, so we're going to look at this in terms of each of the steps involved in our halogenation reaction. Okay, if we look at this overall, we can see that basically, in terms of our delta S term, our entropy term, we're not getting much of a change. We start off with two reactants, we wind up with two products. So not really a big difference in entropy there, right? It's not like you're making a ring compound or something like that either. So so it's probably the enthalpy term that's going to be a little bit important here. Okay, so let's have a look at what affects those enthalpies. All right, so our enthalpy, so we're breaking a carbon-hydrogen bond, and we're breaking a halogen-halogen bond. We're forming a carbon-halogen bond, and we're forming a hydrogen-halogen bond. Okay, so now compare the bond energies that we're breaking here. Imagine we're using methane as our example for our alkane. Okay, so notice that our carbon-hydrogen bond is the same for all of these reactions we're trying out. The bond energy that's required to break certain bonds, you can see it gets a little bit bigger as, or really it gets lower as we get to the larger halogens, right? Those bonds get longer and they're easier to break. In the case of fluorine, fluorine is also unusually low because of the electronegativity of fluorine. The each of those fluorine atoms wants to pluck away one of those electrons. I think that makes that a little bit more stable. Um, so, so you notice that that's going to play a part when it comes into the cost to doing this reaction, right? You also have to consider the reward, the energy that's given off when you form your carbon halogen bonds or hydrogen halogen bonds. Again, this varies depending on the halogen you form. So while it costs less energy to break an iodine-iodine bond, you also get less energy out of forming a carbon-iodine or hydrogen-iodine bond. So something to keep in mind as we look at each of these steps. Okay, so let's look at the overall reaction energy, or the overall delta H for each of these reactions. Okay, so if we swap out our halogen, okay, if we look at the overall change in energy using Hess's law, you can see that for fluorine, chlorine, and bromine, we have overall exothermic reactions. Whereas for iodine, overall, the energy released by forming these carbon iodine and hydrogen iodine bonds is not enough to compensate for the energy it costs to break your carbon, hydrogen, and iodine bonds. So this winds up being an endothermic reaction as opposed to these exothermic ones. Right? Now, the problem with fluorination, of course, is that it's so exothermic that it's really impractical. Okay, that's just kind of dangerous, right? Depending on what you're working with. Also, it's not, even if you can do it relatively safely, like you have to consider that having such an exothermic reaction, having such a low barrier to making this product, means that you're probably not going to stop at just the monofluorine product. You're probably going to have a mixture of products, which makes it, again, less practical in terms of trying to find the product you want or trying to isolate the product you want. Okay, and we've already talked about iodination, why that's also, you're not going to have a spontaneous reaction there. Okay, let's look into more detail with chlorination, bromination. Let's look at how the difference in in our halogen affects the energies of the individual steps of our reaction. So looking at our propagation step, here we are breaking our carbon-hydrogen bond, right? We're doing an abstraction here, and we're also forming the halogen-hydrogen bond here. Okay, so if we look at the difference in enthalpy for those individual steps, you can see that it's exothermic for chlorine and it's endothermic for bromine, right? The second step involves your alkyl radical doing a halogen abstraction. So again, we're forming a carbon-halogen bond and we are breaking a halogen-halogen bond, okay? And for both these cases, this winds up being exothermic. Okay. Now, as I pointed out earlier, like both of these steps are going to be exothermic overall. That's why this is net. It is a net spontaneous process. But that being said, notice that key difference in that first step is very important there. Okay. So for chlorination, both steps are exothermic, right? So again, very important for, in terms of figuring out, in terms of a barrier to your product forming, you have a relatively low activation energy for both your steps. For your bromination, on the other hand, that first step is endothermic. So notice that you're going to have a really high activation energy here because your intermediate is at a higher energy than your reactant. So you're going to have a relatively high activation energy for that first step, even though the second step, of course, is exothermic. So the key takeaway here is that chlorine is going to react more readily. Okay, so it probably has milder conditions. But the thing to consider then is that for bromine reacting, your activation energy is going to influence how your bromine reacts a little bit more. Okay, so to understand this a little bit more, let's talk a little bit about the regioselectivity of halogenation. All right, so because I think this selectivity, this difference in activation energy, is going to be a big part in the selectivity of these two halogens for making particular products. Okay, so let's have a look at propane here, right? So if we have, if we look at the different types of hydrogens, we have these hydrogens on our terminal carbons, okay, which are identical, and then we have hydrogens on our central carbon here, okay, and those are going to be different from those other ones. So if you were going to look at these two different types of hydrogens, right, and ask yourself, if chlorine were to swap out these hydrogens, what would our ratio of products be? Well, you'd look at this and you'd say, well, I've only got 2 of these central hydrogens to swap out, okay, and I've got 6 of these terminal hydrogens to swap out. So in terms of ratios, I've got 3 times as many opportunities to swap out these terminal hydrogens. So looking at these two products, you would expect, oh, I should probably get more, or like from a probability standpoint, I would expect more of this product over here on the right, all right, where a terminal hydrogen has been swapped out. Okay, but keep in mind, of course, there's a difference between the type of radical you form. Okay, notice that here the hydrogen has been abstracted from your middle carbon. Think about the type of radical that would make, right, versus this terminal one. And we see that influence in the distribution in products, right? We have more of that middle carbon having the chlorine due to the secondary radical intermediate you go through, of course. All right. Now, that being said, please also note that you still have a relatively large percentage of your minor product. Okay, so that's something to keep in mind, and we're going to look at that regioselectivity now. Okay, so let's look at why we get these different products. So, again, with I pointed out that there's central carbon gives you a secondary radical, which is going to be more stable than the primary radical you'd get from a hydrogen being abstracted from that terminal carbon. Okay, so that's going to influence, your which pathway you go down. Obviously, this has a lower barrier to, a lower activation energy barrier. Okay, and of course that intermediate's also a lower energy. Now, look at the bromination process, right? Notice that our distribution, while we still see the same net effect, like this is the major product, of course it is, but look at the distribution here. We have almost all of our product being that central, having the bromine on that central carbon. Very, very little comparatively is our minor product where it's on that terminal carbon. Okay? So that's a huge difference when it comes to regioselectivity. Okay? And it all comes back to that first step, right? That formation of that radical, that's our intermediate over here. Okay? That's the alkyl radical we make. In the case of bromination, because that step has such a high activation energy, it's so, you have such a high activation energy, any difference in energy is going to be a huge difference. Whereas for your chlorination, the two relative pathways don't really have much of a difference between them. It's not going to cost that much more energy to make the less stable product. So even though you get less of it, you're not going to get that much less of it. Okay? If you want to see this another way, we could use a Hammond postulate to try and look at this. In the case of chlorination, since you have your intermediates at a relatively lower energy, you can consider your transition state looking a little bit more similar to your reactants. Okay, whereas for a bromination, where your intermediate's at a higher energy, your transition state is going to be closer in structure to that intermediate. Okay, so what does that mean? Well, if we're looking at that intermediate, in the case of chlorination, your intermediate still looks kind of like your initial alkane, right? You're still, you still mostly have this bond together. It's only starting to break, okay? Whereas you still have a long ways to go before this bond forms. But it's the opposite way here. You've pretty much already broken this bond and had your hydrogen abstract over. Okay, so what this tells us then is that your stability of your radical is much more important because you're pretty much already forming this radical in that transition state. The stability of that radical is really, really key to making your product, well, to making that intermediate, which will go onto your product. Okay, whereas for chlorine, it's not as big a deal. Okay, and we can see this here with the different types of radicals we could make. Notice that for chlorine, obviously there's a difference in energy for the radicals. We've seen that tertiary radicals are more stable than secondary, more stable than primary, and that's true. But look at the difference in energy between our transition states. They're also relatively close together. So while this is has the yields like, kinetically it's our best pathway, it doesn't cost that much more energy to go through one of the other pathways. But look at bromination, where we have that first step being so endothermic, right? Now we have a huge gap in energy between tertiary and secondary and primary. So you're really forcing your products through that lower energy state, right? It costs significantly more energy to try and form one of the less stable products. Okay? And that is why bromination is much, much more selective than chlorination. Okay, so that's going to be very, very important when we start using this synthetically, when we start planning out how we want to add, how we want to do a halogenation, how we want to add a halogen to our alkane. You might want to consider what what your products might look like. If you have multiple options for multiple hydrogens you can swap out for a halogen, you may want to go with your bromination just because it's going to be more selective. Now, if you have only one option for if you have only one proton available to swap out, or one site where there are protons to swap out, then having chlorine isn't a bad idea because, like I said, it's going to react more readily. Okay, so for example, if we had, so here we're using a 2-methyl propane here, but if we had 2,2-dimethyl propane, so we had another methyl group over here, then that central carbon has no hydrogens to abstract. You've only got terminal carbons, right? So then chlorination would be fine because you only have one possible product you could make. Okay, but here, if we want to halogenate that central carbon, bromination is the way to go. Okay, whereas with chlorination we'd only get a little over, like about 2/3 of our product would be the product we want. Okay, so as opposed to 100% of the product. Okay, so so that's why generally speaking, but generally bromination is better for selectivity. Okay, so even though chlorination seems like it'd be a good option for because it seems more reactive and therefore it seems like it would be easier to make the product, you have to consider that sometimes it makes things too easy. Okay, this is again the reason why we don't like using fluorine either. Fluorine is very, very impractical, okay, in this respect. Okay, so that being said, let's have a look at all of our possibilities here. So think about the hydrogens present on this molecule and ask yourself also, where are these what are the radicals going to look like? And using the stability of these radicals, try and rank the products that you would make, like in terms of which ones are the most major to which one's the most minor. Okay. All right, so if you've paused this video and have come back now, let's go through the answers. So here are our options. Okay, notice that this site would have been great because it's allelic to this double bond, but there are no hydrogens on that carbon, so that prevents that happening. Likewise, these two carbons aren't likely to form, those hydrogens aren't candidates because they are vinylic hydrogens and therefore unlikely to be abstracted, right? You're not going to form a stable radical there. So that rules out all of those. So you've got these methyl groups here, okay, which are, likely to form there. You've got a hydrogen that's present over here. You've got, of course, hydrogens here and here and here. All right. So let's look at the different options. Okay, so these are not listed in order, so the descriptions are here to the right. So this tertiary site over here, of course, that's going to go through a tertiary radical, so it makes sense that that's the most abundant product, right? Please note that the bromine can add to either side. We saw earlier in this chapter that your radical can interconvert relatively readily. And so it's almost like having a carbocation where it can be attacked from either side. So notice that we get both enantiomers of this product. All right. Next up, we have the secondary site over here. Okay, and that's why that's our second most abundant product. Okay, and that yields our primary sites. Now, why is this location a little bit more abundant than this location? Here it's just a probability thing. There's only 3 hydrogens here to abstract, whereas here these 3 hydrogens and these 3 hydrogens are equivalent. So there's double the number of sites to form this product. Okay, so that's why it's a little bit more abundant than this product here. All right. So something to consider then is the stereochemistry. I just pointed out in the previous in our distribution of products a little bit earlier that we have your radicals can interconvert, and therefore you could have your incoming group, your halogen, add to either side. Well, you've got to consider then that with a halogen adding on, if you have multiple like different types of groups coming off that carbon, you've now made a chiral center. Okay, because for example here you've got 2 hydrogens. If you swap one of them out for a chlorine, well, now that carbon's a chiral carbon. It's got a chlorine, a hydrogen, a methyl group, and an ethyl group, right? So it's something to keep in mind about stereochemistry. Right. So that being said, of course, like I said, you will form a racemic mixture. Like out of these 2 hydrogens, either one of them can be abstracted. That's not important, but the resulting radical can have the chlorine attack either side. Okay, so that's going back to an earlier slide I pointed out. Again, you have that rapid interconversion, that rapid inverting that allows your radical to be attacked from either side. Okay, and so that's why we get a racemic mixture of our secondary product. All right, so go ahead and try out another problem that's very similar here. We're going to look at 2-methylbutane. Okay, so draw that out and figure out what products we'll have there. So go ahead and pause the video right now, and we'll come back with that answer. Okay, so here's the answer to that question. So of course there's 2-methylbutane, and of course notice that we have a tertiary site there. So keep in mind that that's probably going to be your major product that you're forming as well. But of course, this being chlorine, you're probably going to form, get a decent percentage of the minor products as well. We've got a secondary one here. We've got primary ones here and here. Please note, of course, though, that the secondary product has that's a chiral carbon where that chlorine joins in, right? We've got a hydrogen, a methyl group, and an isopropyl group. For this primary product, you've got 2 hydrogens here, so that's not going to have an enantiomer. Likewise, for the tertiary product, you've got 2 methyl groups coming off that carbon, so that's not going to have an enantiomer. This one is probably the tricky one that I'm guessing a lot of people missed. Even though you have 2 hydrogens here, the thing to note is that this carbon is chiral now, because you have a methyl group, you've got a hydrogen, you've got an ethyl group, and then of course this carbon is no longer a methyl group. It's got a chlorine on it, so that makes this group different from this one. And so now this carbon, which is kind of not really touched in this product, but that carbon now has become chiral. Okay, so I'm guessing if any of you missed a product, it was probably this one having an enantiomer. So watch out for that. All right, in this reaction here, we're starting off with a chiral center. Notice that our carbon over here has a methyl group, an ethyl group, and a propyl group coming off of it, and a hydrogen, of course, which is not shown. But this, when we do a hydrogen abstraction, is going to be the most stable radical. So it'll be a tertiary radical that we'll add our bromine on. And you can see here we get that resulting product. Now, the question here is this going to have a preference for one enantiomer versus another? Because after all, here we have the S enantiomer, right? Are we going to get the S or R enantiomer here? And the answer, of course, is that you're going to get a racemic mixture. Don't forget that when the radical forms, it's going to be a shallow pyramid. So for all intents and purposes, it's going to be essentially trigonal planar, even though technically it's not, because that bromine can add to either side of that carbon. Okay, so you'll get a racemic mixture of products here. So that's why stereochemistry isn't being shown in this product, even though this is a chiral center. You're going to get both enantiomers as your product. Okay, let's try another one out here. So here we have, a molecule, with multiple tertiary sites. Go ahead and draw out all the monosubstituted products that we'd form here. Okay, and then ask yourself, are we going to form, are we going to have, when we look at some of the pairings that form up, decide if they're enantiomers, diastereomers, or what have you. All right. Here are some of the products. This is not all of them, of course. So you can see that we've got the two tertiary products, right? We've substituted the hydrogen that's at this point here and at this one here. Okay, so these are both probably two most common products, at least. And of course, you can swap out these primary hydrogens on your methyl groups over here to make either of these two products. Now, if it's not clear why you've got enantiomers here, you have to remember that while these two methyl groups are equivalent here, once you add a bromine on one of them, they're no longer equivalent, and this carbon becomes a chiral center. You've got a hydrogen, a methyl group, you've got the ring, and you've got this carbon with a bromine coming off of it. That's 4 different groups. You've got a chiral center, and so the orientation around that chiral center is important. Okay, and so you can get it's an enantiomer accordingly. All right. If you're having trouble seeing that, you could think of it as either one of these methyl groups being, having their bromine added to it. Depending on whether you picture this hydrogen that's not shown as pointing towards you or away from you, and then rotating accordingly, you'll get the two enantiomers if you attack either of these methyl groups. Okay, now we haven't looked at any of the substitutions on the ring itself, of course. These are secondary sites. So let's have a look at the molecules that form when we swap out one of their hydrogens with bromines. Okay, so here are all the possibilities for that. And this, you can see, it makes an interesting mix of enantiomers and diastereomers. So this is kind of what that question was getting you to think about, the stereochemistry involved when you compare all of those products, right? We've got lots of possibilities here, right? So here here are all the different combinations that we'd form. Out of these 8 products, each of these are enantiomeric pairs, okay? Basically, if it's kind of shown that, depending on if we compare this molecule and this molecule, these two, you have the bromine adding on opposite sides, right? But they wouldn't be enantiomers of each other, right? Because due to the stereochemistry, that chiral center over here, right? This carbon now has become chiral because this ring is no longer symmetrical. That's something to consider here. So really, it's when you attack your carbon from from the top of one side. I guess if you attack it from the top of the other side, this carbon is would be equivalent when this molecule is symmetrical. But if you get it from the other side with this methyl group pointing up, you can see that these two molecules are mirror images of each other. It's kind of hard to see because they're not directly on top of each other. But if you basically imagine your mirror plane kind of going like this, okay, like here's your mirror plane, and you slide this molecule down a little bit so that this bromine is lined up with this bromine, it would then become apparent that the two molecules are mirror images. And that's kind of what's going on for all of these enantiomers. Okay, and then of course the arrows show how things are related as diastereomers. So basically, you can kind of see that your isopropyl group and your bromine are at the same positions here and here, but instead of being up up, here we have up down, right? Or rather, R and S enantiomers, R and S stereochemistry at those chiral centers. Okay, and that's the difference between all of these, right? So here we have up up, here we have up down at those same positions, and so on. Okay, and that's why those are all diastereomers of each other. Okay, so we mentioned earlier that the allelic position is just primed for being, having a halogenation, right? We get a particularly stable radical at that site due to the resonance that's involved. Okay, so want to just jog your memory again. Note that the bond dissociation energy over at our allelic site is the lowest out of our three options there. At the vinylic site, of course, it's the highest because that's really, unlikely to form. There's not going to be a stable radical. And then, of course, just the regular secondary site at the bottom there in green, that's our, that has a moderate bond dissociation energy. Right. So, of course, that allelic position in blue, that's going to be the site that we're probably going to halogenate. Okay, we've seen that, we have a resonance stabilization off that site accordingly. Okay. All right. Something to keep in mind for overall, for when it comes to this reaction overall, keep in mind you're starting off with an alkene and you're reacting this with bromine. Keep in mind that this could undergo an addition reaction, right? You could add bromine across that double bond. It'll do that anti-addition that we saw back in our chapter on alkenes and addition reactions. So something to keep in mind there. I think in that chapter, we specifically said we'd use carbon tetrachloride as our solvent. And you may have noticed at least once or twice, I did we see that the conditions mention that we do that reaction in the dark. The reason for that is that we need light to encourage the halogenation radical reaction. Because remember, this mechanism involves first turning our bromine molecule into bromine radicals, and you need light for that. So if you do this reaction in the dark, you'll only get the addition product. Okay, so something to watch out for if you're doing this reaction in real life and you're considering like synthetic applications of this. Okay, now to avoid getting the addition reaction, right? If you, so if you're doing this even in the light, you still have, bromine molecules that can still do that addition reaction, and that's going to give you a competing product and therefore decrease your yield of the product you want, right? So one way to avoid this is to provide bromine radicals exclusively. Don't use bromine, which can undergo that addition reaction, but instead provide bromine radicals directly. So the way we do this is to use a molecule called N-bromosuccinimide, also known, just abbreviated as NBS. So succinimide is this sort of amide, right? You've got a nitrogen that's next to carbonyls, and we have a bromine attached to the nitrogen off that amide, amide, I guess is the proper pronunciation there. We'll have a long discussion the difference between amides, amides, and amides. It's three different pronunciations for the same spelling of a word, which gets kind of confusing in organic chemistry, but I'm sure we'll talk about that later on in next semester in the chapter on amines. But anyway, so here we have an amide, and the bromine's attached to that nitrogen there, so that's where the N in that name comes from. Okay. So anyway, this is a good source of bromine radicals because this resulting succinimide molecule is resonance stabilized. All right, so we only have our bromine radicals. So that's our initiation step, and then of course our propagation step is what you would expect. You have a bromine radical doing a hydrogen abstraction, so it pulls off hydrogen bromide, which is one of your products. The resulting resonance stabilized allelic radical, of course, can then react with a bromine molecule and pluck off the a bromide to a halogen abstraction and produce our other substitution product. And of course now we have a bromine radical again, which can repeat that first step, and you have a chain reaction. Okay? So again, you want to minimize that addition reaction. That's why we used NBS in the first place. So you probably don't want to use a lot of bromine. So generally, typically, you keep the concentration of bromine relatively low here. Okay. So the succinimide radical that we saw earlier, that can also undergo the propagation step if it collides with HBr. So you might want to watch out for that. But again, assuming you have relatively small amounts of that, hopefully this should be minimal. Okay, so now here's another example of an allelic halogenation. All right. Now notice that we have two sets of products here. Okay. Again, this has to do with the fact that we have an asymmetrical, allelic molecule. We didn't. We had a lot of symmetry with our previous example, so you didn't quite see this. But over here, you can see that this molecule is kind of asymmetrical to begin with. So take a second and pause this and think about what your radical looks like when you do your hydrogen abstraction, and ask yourself, how does the resonance structure of that allelic radical yield both products? All right, I'm just going to draw this a little bit more simplified. So again, you have your NBS, which produces your bromide radical, which does a hydrogen abstraction. I think most of you probably figured out that this tertiary site that's also resonance stabilized is probably where your hydrogen abstraction is going to occur, right? So your bromine radical pulls off that hydrogen. So the resulting radical you get, okay, so I'm not drawing the full mechanism, just drawing the abbreviated version here. That's the radical that we're going to produce, right? And of course, when this does a halogen abstraction of the bromine, that'll give you this product here. So how do we get this product over here? Well, remember, you can have a resonance structure where we get an electron, our radical electron moving over here, and this pi bond cleaves so that one electron goes and forms a pi bond here, and we get a radical over here. So this is the other resonance structure we see. So a double bond forms here, and here's our radical. Now, if this does a halogen abstraction, that's where we get this product over here. Okay, so I haven't drawn the full mechanism, but this is basically where our two products go. So we do a halogen abstraction here, and this one does a halogen abstraction to give us this product. All right, now we've so far mostly looked at substitution reactions, involving halogens. Now, and we kind of talked briefly about how oxygen is is heavily involved in radical reactions due to its ability to form a diradical, right? When you cleave that pi bond between your two oxygen atoms in your oxygen molecule. Well, part of this is both of these factors are going to come into play here when we look at reactions involving ozone. All right, ozone forms very readily, especially in the upper atmosphere, in the stratosphere, due to the fact that the stratosphere doesn't have much blocking sunlight from it, or especially some of the higher energy wavelengths from the sun, so more of the UV rays and things like that. And those high energy wavelengths from the sun cause oxygen to undergo a radical reaction and form ozone. So that's why we have an ozone layer in the stratosphere. Okay, so we essentially keep on having, we have this sort of cycle where ozone constantly forms, or rather where oxygen and oxygen radicals or oxygen atoms constantly form ozone, and at the same time that ozone decomposes back into oxygen molecules. Okay, and this is one way that the ozone layer kind of protects us from that harmful, higher wavelengths like UV, because it pretty much absorbs that radiation to form oxygen. Okay. So yeah, so essentially, this is a entropy just kind of this is a spontaneous process, right? We're increasing, we're making producing heat as a product here, which goes along with the second law of thermodynamics. Okay, so I also mentioned that chlorine radicals come into the picture here as well. One thing to realize with with the ozone layer, as I mentioned, it helps absorb that UV radiation from the sun and prevent it reaching the Earth's surface. Well, in order to disrupt that cycle where ozone's cycled into oxygen and oxygen back into ozone, we need to insert some radicals into that process. But these radicals have to meet two requirements. One, they've got to come from compounds that are stable enough to reach the upper atmosphere, to reach the stratosphere where these reactions take place. Two, once they're in the stratosphere, they have to form those radicals. And of course, these radicals will then interfere with that process. And it turns out that chlorofluorocarbons, that's organic molecules that have chlorine and fluorine attached to carbons, are prime candidates. They meet both these requirements. They're very stable molecules, which is why they were, used in the first place. We use them as refrigerants, and being very stable, they're not going to undergo any reactions, and that's a great thing, right? You don't want them reacting with anything. You want them to just stay there and absorb heat, right? But it turns out that they are stable, and they will be very stable, and they'll make their, due to their stability, they'll make it all the way up to the upper atmosphere. But once they interact with light from the sun, especially those higher wavelengths, now you start making these chlorine radicals. And these chlorine radicals, as we've seen in all of our other reactions, are capable of engaging in chain reaction propagation steps, where they're essentially working catalytically. Okay, and these radicals are going to interfere with our ozone formation. Okay, so how do we prevent this phenomenon happening? Because obviously we still need refrigerants. These chlorofluorocarbons are really, really useful molecules, right? They're way better than all of the, and way safer actually than a lot of the other refrigerants that people typically use before, right? But obviously we can't use them because we need our ozone layer. So we can tackle this problem from either one of those two requirements. The first one is that chlorofluorocarbons are too stable. They're stable to the point that they can make it all the way to the stratosphere with those chlorines still attached, so that they're still there ready to form radicals in the stratosphere. If we use, instead of using chlorofluorocarbons, if we use hydrochlorofluorocarbons, these molecules are a little bit less stable. So they will decompose before they get to the stratosphere, before they get to that ozone layer. Okay, and so therefore they don't make it to the stratosphere. All right. The other alternative is to just not have chlorine radicals. So instead of using chlorofluorocarbons or even hydrochlorofluorocarbons, we use hydrofluorocarbons. So we take chlorine completely out of it. Okay, so now we don't get these really stable chlorine radicals that stick in the stratosphere and catalytically destroy the ozone layer. Okay. Other applications of radical chemistry involve, just understanding how combustion reactions work. I think we're all familiar with combustion reactions. It's a very, of course, it's really common for any hydrocarbon, to burn in oxygen. But what's the mechanism by which hydrocarbons burn in oxygen? Well, it's essentially a radical process. There's a radical reaction that governs that process, and basically, if you want to fight fires, one way to do that is to interfere with that radical reaction. Okay, so to understand this, first of all, essentially you're starting off with a fuel, right? You need a fuel, you need oxygen, and you need heat. Those are the three elements that cause a fire, right? Well, so basically, if you take your fuel and you heat it with enough energy to break bonds homolytically, now those radicals are free to form our products. So the oxygen-hydrogen bonds of water and the carbon-oxygen double bonds of carbon dioxide. Those are your typical products in your in a combustion reaction. Okay. Now, of course, those resulting molecules are relatively stable. Those release even more energy, right? Combustion reactions are exothermic, and of course, then you're providing more energy to break more bonds homolytically and essentially carry out a chain reaction again. Okay. So basically, if we can disrupt the formation of those radicals, or disrupt those radicals, or stop them being radicals, stop them staying radicals long enough to form carbon dioxide and water vapor, that would generally, that can help put out your fire. Okay. Of course, there are other ways of fighting fires that we've seen before. Water, of course, has traditionally been used to put out fires. It has a really high specific heat capacity. It absorbs a lot of energy and therefore quenches the reaction that way, right? Other ways to do this is to take a very dense gas, denser than oxygen, and therefore blanket the reaction that way. So carbon dioxide and argon are dense neutral gases, inert gases that prevent, that don't react with your fuel and prevent oxygen getting to your fuel. Okay. The third method, of course, now, as I mentioned, we can disrupt the radicals in our reaction, and this is where halon fire suppression agents come in. Okay. Basically, well, they work through the other ways as well, of course. They're relatively dense, so they can smother the fire just like carbon dioxide and argon do. Okay. They can absorb energy just like water does, using the energy required to break their carbon-bromine bonds. Okay. But the third way is that when they break these bonds, they form radicals. These radicals can combine with the radicals in your fuel that stop it reacting with oxygen to make your combustion products. Okay, and therefore that's the third way that these halons help suppress combustion. Okay. So, of course, halons, as we see, we've got carbon and we've got chlorine attached to that, and fluorine, right? So they would be like chlorofluorocarbons, but having bromine on there kind of helps a little bit. Of course, now the resulting product you've made here is a chlorofluorocarbon. So again, we've just seen that that's probably not the best thing to have for the ozone layer. All right. So an alternative here is to, as we saw earlier, is to leave out the chlorine and just use only hydrofluorocarbons. Okay, and that's what we have here with FM200. Okay. I mentioned, continuing in this vein of oxygen taking part in radical reactions. I had mentioned that oxygen is a diradical and therefore will react with radicals, or generally sort of insert itself into a lot of radical reactions. One of the problems with that, though, is that you can then have auto-oxidation, right? Where basically, since oxygen's so abundant in our atmosphere, it'll readily react with molecules that can undergo a radical reaction. So, for example, look at cumene over here, right? You've got a benzylic tertiary site that's primed for hydrogen abstraction, readily forms a radical, or would readily form a stable radical there. Well, it can then react with oxygen, and oxygen will insert itself, between it and a hydrogen in there. Now, despite that readiness for oxygen to react here, this process is still relatively slow. Okay, so let's look at this whole process and think about what things can speed this up. Again, why, of course, that's going to make this kind of a problem. All right. So, of course, here's the full mechanism, right? We start off with our cumene. It loses that hydrogen at that tertiary site, makes a relatively stable radical. The radical reacts with oxygen, makes the corresponding peroxide radical, which can then do a hydrogen abstraction and make the peroxide product that we see. Okay. So here's the overall process as we saw it, right? We had cumene reacting with oxygen to make our peroxide. Okay. So now, in the case of cumene, of course, that's not a huge issue. But for some molecules, this can be really dangerous. So there's certain hydroperoxides, like in this case with the one that forms with diethyl ether, that make this that make a relatively explosive product. And so that's why these molecules don't have a long shelf life. Not only because they don't last long, but it's dangerous to keep them on the shelf that long, where they gives them more of a chance to form these explosive byproducts. Okay, so typically when you buy ether, even the ether that you see in our stockroom, when we buy it, we'll date it and keep it on the shelf and make sure that we get rid of it before it's before too long, right? Typically, we only order ether right before we need it for a lab for this reason. Okay, so how, if this is a slow process, what speeds this up, right? Of course, we've seen that light is, kind of key for producing radicals and getting that initiation state working. So one way to slow this down further and try and prevent it or hold it off as long as possible is to use a dark container. That's why you've probably noticed a lot of reagent bottles tend to be brown, right? They tend to have dark glass, okay? Ether actually comes shipped in metal containers so that light doesn't make it through to the contents at all, okay? So typically you use very dark containers or opaque ones at least to help, opaque or translucent ones as opposed to transparent to store some of these molecules. Okay. Yeah. Yeah. So especially you want to watch out for things like, cumine's of course another, like an example there where you've got a benzylic hydrogen which kind of can make make things a little tricky in terms of shelf life. Okay. Another good example of this is just with food in general, right? Like why does butter go rancid, for example? Why does food spoil? One way that food can spoil, not just from bacterial activity, but here you can see we have a triglyceride, right? This is a lipid. So you've got all sorts of a lot of these things found in just food in general with any sort of fat, right? Whether it's animal or vegetable fat. But let's say you have butter, okay, which has a lot of these triglycerides in there. But let's say especially you have butter with a lot of unsaturated fats in it. Now, unsaturated fats are those that have unsaturated carbon change, which means there's a double bond in there, right? That's where the unsaturated part of the name comes in. Well, if you have a double bond, the carbons next to it are allelic positions, right? Which means that they are primed for this substitution of this insertion, this auto-oxidation step. Okay, so you want to watch out for that because again, that can lead to the food becoming going bad. So how do we prevent that? This is where preservatives come in. Okay, so if you've wondered why, what preservatives actually do, one role of certain preservatives such as BHT and BHA is to effectively soak up radicals and stave off auto-oxidation. Okay. So you can see here that if you look at either of these preservatives, they're kind of doing something similar to what we saw with hydroquinone earlier in this chapter, right? They'll react with a radical where the radical will pluck off a hydrogen, but the resulting leftover molecule is resonance stabilized. So it kind of readily gives off a hydrogen to sort of soak up those radicals and prevent them reacting with the food. Okay. All right. So now, while those preservatives are antioxidants, we have a lot of naturally occurring molecules that are antioxidants as well. Okay, a lot of vitamins like vitamin C or vitamin E are antioxidants as well. And you can kind of see that in terms of the the allelic oxygens that we have with or allelic alcohol groups that have a proton that would produce an oxygen radical that's resonance stabilized. So actually, if I go back to BHT, you can see that here, right? We have an OH group that's that's sort of kind of like a phenol, right? It's coming off our benzene ring. But more importantly, it's kind of at an allelic position, right? We have our OH group here coming off our our double bond, right? So that hydrogen's at an allelic position, that oxygen's allelic, right? And so this is a particularly stable, like a resonance stabilized radical that we can use. So in the same way with our vitamins, vitamin C, vitamin E, we also have these resonance stabilized hydrogens, right? We've got one here. I could have also done, this one over here, right? So we've got that's readily available. Okay. Similarly here we have our our phenol group. Like we've got an alcohol group that's coming off of a benzene. Okay, and we've got that resonance stabilization for the resulting radical. If you recall back in chapter 9, we talked about Markovnikov's rule when we looked at the addition reaction of hydrogen halide, right? So hydrohalogenation across an alkene. We noticed that just adding our hydrohalide, we would have our hydrogen go to our less substituted carbon and our halogen go to our more substituted carbon. That was Markovnikov's rule. But I pointed out back then that if we throw in a peroxide, okay, we instead get an anti-Markovnikov addition. Our halogen instead goes to our less substituted carbon. Okay, and we didn't go into the mechanism there because we still had to understand how radical reactions work. And, well, now it's that time. So let's look at this mechanism and understand why it happens. Though I think hopefully by now you've probably realized that a peroxide, as I mentioned earlier, is a great candidate for an initiator for these radical reactions, right? They readily cleave at that oxygen-oxygen bond, and you make, these alkoxy radicals. So you can imagine that that's going to be our initiation step here. Right, so with that, we have our initiation step where that oxygen-oxygen bond homolytically cleaves. Now, of course, you don't necessarily need a lot of that radical because it will then go on to a hydrogen abstraction and form your bromine radicals that will go on to the propagation step that we're going to see. All right, so our bromine radicals will do an addition to our pi bond in our alkene. Okay, now which carbon do you think our bromine's going to add to? Okay, well, here it's shown adding to this carbon over here. All right, so when we finish with our addition step, notice that this radical shows up on the other carbon of our of what used to be our double bond. Well, notice that this is a tertiary radical. What would have happened if the bromine added to the more substituted carbon following Markovnikov's rule? Well, our radical would show up on this carbon on the left, which would have been a secondary radical, which would be less stable. So it makes sense then that bromine is going to add to your less substituted carbon to give you this more stable tertiary radical. Okay, and of course then in the second step of propagation, this radical then goes on to do a hydrogen abstraction to make the product that we see. Okay, and of course we yield another bromine radical to repeat the chain reaction. Okay, but the important thing to see here is this is why we get that anti-Markovnikov product, right? So what's the difference here between this mechanism and the hydrohalogenation reaction we've seen before? Well, in that reaction, right, in the hydrohalogenation, right, using our ordinary addition reaction, here, let me show you with an example here, using the same alkene. If you recall, we have our HBr also provide our, it's going to act as our acid here. It'll do a proton transfer. So we'll have our alkene pick up our hydrogen, right? Now, which of these two carbons is going to get the hydrogen? Okay, in the same way that this less substituted carbon picks up the bromine to make this tertiary radical, this alkene causes this less substituted carbon to pick up the hydrogen to make a tertiary carbocation. Okay, so we lose a bromide ion in the process, and we are left with this hydrogen added on here. Okay, and notice we have a tertiary carbocation. If the hydrogen added to the more substituted carbon, we would have had a secondary carbocation, which is less stable. Okay, so it's the same reason why we don't see the secondary radical, why the bromine adds over here. All right? So what's the difference here between these two? Well, in the case of our addition reaction, the first step involves a hydrogen going to that less substituted carbon. Whereas here, the first step in our propagation for our radical reaction involves our bromine radical going to that less substituted carbon. So in addition reactions, we have hydrogen first, bromine later to the carbocation. In a radical reaction, we have the bromine first, and we have a hydrogen going to that to that tertiary site later on with a hydrogen abstraction. Okay, so it's really an order of operations difference that causes the anti-Markovnikov product forming. Okay. All right, and then of course the termination step is just your typical termination steps, right? You have your coupling reactions between your bromine radicals. Okay, let's look at the thermodynamics of these addition reactions, just as we looked at the thermodynamics of the halogen substitution reactions. Okay, so typically with HBr, all right, hydrogen bromide, we typically use that for our radical addition, for our anti-Markovnikov radical addition, right? That's a spontaneous process. What about using HCl or HI? Okay, well, it turns out those are not spontaneous, right? Those are, they don't yield the product, right? They just tend to go favor the reactant side. In other words, the reaction doesn't happen. Okay, so why is that? Why do we only do this with HBr, and why doesn't it work for HCl and HI? So in the next few slides, let's look at look at the thermodynamics of this process to understand how this works. Okay, so again, with your Gibbs free energy equation, remember we have our enthalpy term and our entropy term, right? And so we want to look at the competition of those two. Ideally, we'd have both of those be negative, but let's see what happens here. Okay, let's break this down to our different steps. So in our first step of our propagation, we have our addition to that pi bond, right? We have our halogen radical coming in, and it opens up that pi bond and turns it into a carbon radical. Now, what bonds are we breaking and forming, right? We're breaking a pi bond here, and we're forming a carbon-halogen bond. Now, in the case of chlorine and bromine, right, those are relatively, those are relatively high energy bonds we're forming, and so we're going to have an exothermic process for that. In the case of iodine, though, that long carbon iodine bond isn't high enough in energy, doesn't release enough energy, so that the overall enthalpy term is going to be endothermic for that step. Okay, the entropy term I think is pretty straightforward, right? You've got two reactants making one product. That's a decrease in entropy. So with the negative sign in negative T delta S, that your entropy term is going to be a positive number, or a positive term for all of these. It doesn't really matter which. Okay, so with that being said, here you can automatically rule out hydrogen iodide, right? Because of the fact that both these terms are positive, delta G is going to be positive, and that's going to be non-spontaneous. Okay, so that only leaves HCl and HBr to consider. So let's have a look at what happens with those. Okay. All right. A quick note here before we move on. We still have a competition between our enthalpy and entropy terms here. So keep in mind that we still want to minimize that entropy term to avoid it getting, to interfering too much with the exothermic side of this, right? Or competing with that negative enthalpy term and influencing delta G. So if we have to do this at a low enough temperature, it will allow delta G to remain negative. Okay. Now, what about the second step of this reaction? Well, in the second step, we're going to break a hydrogen-halogen bond, and we're going to form a carbon-halogen bond. Now, in the case of hydrogen iodide, though we've already kind of ruled this out because of that first step, this costs very little energy. This hydrogen iodide bond is relatively weak, relatively easy to break. That's why this is an exothermic step, right? In the case of HCl, though, this is a relatively strong bond. It costs a lot of energy to break this, relatively speaking. And so even though all three of these molecules form the same carbon-hydrogen bond, in the case of HCl, this is going to be an endothermic step. Okay? The entropy term for this is going to be roughly 0. It doesn't really matter. We have two reactants making two products, so it's kind of a moot point from an entropy standpoint. But the key thing here is that the enthalpy term for HCl is going to be positive, which means delta G is going to be positive for the second step for HCl. Okay, so that kind of throws off HCl. And so that's why really our only realistic candidate for this reaction is HBr. Okay, so yeah, so that's why when you see this anti-Markovnikov addition using a peroxide, you've probably noticed that we always use HBr. We never use any other hydrohalogens. So this is the reason why. It's just not practical to use any of the other hydrohalides. Okay. Other things to consider. We kind of saw this back in the chapter on addition reactions, but if you recall, when we do our addition reactions, we've looked at regiochemistry, right, with where our bromine goes, right, and you're looking at the Markovnikov versus the anti-Markovnikov product. But the thing to consider is that halogen can turn your carbon into a chiral center. Okay, so basically, this carbon has a methyl group, a bromine, a hydrogen, which isn't shown, and then this isopropyl group. So that's going to be a chiral carbon now. Okay, so that's something to keep in mind for the, from a stereochemistry standpoint. So are you going to get, which enantiomer are you going to get, basically, right? Well, keep in mind, of course, that bromine can add to either side of this carbon, right? This original alkene is trigonal planar, right, with the hydrogen sticking out here. That's a trigonal planar site. The bromine can add on to either side of it. So you're going to get a racemic mixture of products. Okay. Another application of radical reactions is with polymerization. Okay, we can take alkenes and link them together to form polymers. Now, there are multiple ways you can do this polymerization. You can do this through a carbocation intermediate. You can do it through a carbanion intermediate. You can use a catalyst that does metathesis reactions. All sorts of neat ways to do this. But one common way of doing it is through a radical intermediate. And so we're going to look at that mechanism for radical polymerization. So first thing about, what is a polymer, right? If you're not familiar with polymers, polymers are long chain molecules with repeating units. Now, we call each of these individual units monomers, right? So a monomer is a single mer, and a polymer is many mers, so to speak. Okay, I think mer here referring like the word isomer. We're talking about a molecule, right? A small molecule. So with a typically you're going to have a monomer that has a pi bond in it. Okay, we're going to see that what grows our chain, what propagates our chain, so to speak, will involve addition to this pi bond. Okay, so we start off as always with some radical initiation step. So it helps to have a little bit of peroxide, for example, or some simple, some easy to form radical, and we then use that with our with one of our monomers, and it generates that first radical that's going to be involved in our propagation step. So what happens in our propagation step? This radical is going to attack another alkene monomer. It does an addition to the pi bond, and it kicks that radical to the end of that carbon chain. Well, that's going to attack another alkene monomer, which will kick that radical to the end of that carbon chain. And you can see that for every addition step, we keep on growing this growing carbon chain by 2 carbons. Okay, so you're just going to keep on adding carbons 2 at a time, and this chain will get longer and longer. Okay, and as long as you let this propagation go on, that determines the length of this carbon chain. Of course, you can then get to the termination step, where you have coupling reactions. Either you get another one of those radical initiators to cap off your carbon chain, your polymer chain, or you can get 2 polymer chains to sort of cap off each other. Okay, but in both cases, you have a coupling reaction which terminates the reaction. Okay, of course, like, depending on your ratio of initiator to monomer, that probably controls how much, how long your carbon chains can grow before they get terminated. So that controls your polymer chain length. Okay, so there's ways to control that. But yeah, so the process we just saw involved a primary radical, which we've seen aren't particularly stable. So even though I use that for illustration purposes, typically we're going to look at monomers that have more substituents on that alkene. Okay, we'll see some examples in a second. Okay, and like I mentioned, there are other reactions that can do this, and so since primary monomers aren't really good candidates for these, whether it's a radical addition or even if we go through a carbocation or carbanion intermediate, right? Those aren't particularly stable. So if you want to use a primary monomer, one way to do this is to use a catalyst of some sort. So if you want to skip ahead to later on in your textbook, in chapter 27, it does go into detail on some of the catalysts that can carry out these polymerization reactions. Okay. Other things to watch out for in radical polymerization. It is possible to abstract a hydrogen from somewhere in your carbon chain, not necessarily just grow from the radical at the end. Okay, so here we have a completed, polymer chain, but remember, you still have radicals floating around everywhere, right? So a radical can do a hydrogen abstraction and turn this into an alkyl radical. Well, this radical can then go on and do its addition reaction, and that's where you get branched polymers. Okay, so branching is important. You can get all sorts of neat polymers that way. All right, so and that can change your properties of your polymer. It definitely changes the rigidity of your resulting material. Okay, if you're wondering why that's the case, you've got to think about intermolecular forces, right? So when you minimize branching, you get more rigid materials. Keep in mind that then you're getting straight chains, right? Especially if you're using, let's say, a primary monomer of some kind using a catalyst. Well, in that case, these straight chains can really stack against each other, and keep in mind how long these molecules are, right? That's a lot of London dispersion force interactions between those carbon chains. Okay, so what kinds of polymers can we form from different types of monomers? Well, you can actually figure out the name of your polymer from the common name of your monomer. So, for example, here we have propylene, right, which is the common name for propene. Okay, so propylene is the old common name. So polypropylene is just that polymer that you form when you open up that double bond. By the way, you'll notice that to represent polymers, rather than drawing a long chain, it's pretty common to just draw the monomer with the double bond opened up and the bonds from those carbons extending beyond these square brackets. Okay. Sometimes you'll see a number put here that tells you the average length of your polymer chains, but otherwise you'll just see an N there for just a generic polymer. Okay, so polypropylene here shows, you've got your alkene, and you can see what's attached to it. All right, just showing, these carbons have 4 bonds, right? They're sp3 hybridized carbons. One bond is going, from this carbon's going on to continue the chain that way. One bond's going this way to continue the chain to the right. And of course there's a bond between them. So each of these carbons has 2 other bonds, right? So it's what's on these other four bonds that differs these different polymers. So in the case of propylene, we have a methyl group coming off of this carbon. In the case of styrene, that's a benzene ring or a phenyl group. Okay, and that's where we get polystyrene from. Okay, here we have vinyl chloride, right? That's the common name of 1-chloroethene, right? And so vinyl chloride will give you polyvinyl chloride or PVC. Okay. Here we have tetrafluoroethylene, which is the common name for 1,1,2,2 tetrafluoroethene. Well, when you open that up, you get this polymer. The trade name for this polymer is Teflon. Okay, this is what Teflon is made from. It's basically just the polymer of this alkene. All right. So again, very, very useful stuff when it comes to polymer reactions and the products you can make from that. Other processes that take advantage of radical reactions include cracking and reforming of crude oil. We talked about crude oil way back when we talked about hydrocarbons in general. We talked about alkanes and alkenes. So I may have mentioned back then that certain particular lengths of carbons are more useful than others. Considering like how much gasoline is consumed on a daily basis, it makes sense that you want to shorten some of your longer carbon chain lengths into hydrocarbons that are in that range for gasoline, right? So we do so that's where cracking comes in, right? You take advantage of a radical reaction to break up these longer chains into smaller chains. So you can see that here, for example, we do an elimination. Okay, remember that's the opposite of our addition to a pi bond. So basically, if you have a radical present in your long carbon chain, you can basically cleave at one of these bonds and form a pi bond accordingly. Okay, notice your product here is an alkene, all right? But the bottom line is you've made a shorter chain molecule, okay, or rather two smaller chains. Okay. In the case of reforming increases the branching in your product. So again, to do this, you need a radical, right? You can form a radical somewhere in the middle of your chain, and that causes, you can basically have two of these radicals come together and form, this branched molecule. Okay. I've mentioned a couple of times when we talked about halogenation that it's a very useful tool. Alkanes are not very reactive, and so bromination, or just halogenating these in general, whether chlorination or bromination, it's going to add a functional group to something that's not very reactive. Okay, and then once you've got that halogen on there, whether it's a bromine or chlorine, now you can do a whole bunch of reactions with this molecule. If you have a chlorine or bromine, remember that's a great leaving group. That's going to be great for doing substitution reactions, for doing elimination reactions, and then with those products you can go on to do other things. Okay, but that's why if you are starting off with an alkane, right? If you're given a synthetic problem involving an alkane, chances are your first step is going to involve a halogenation of some sort. Okay, that's just a very common tool to have in your synthetic toolkit that we're going to use. The next chapter, we're going to spend a lot of time talking about syntheses and how to approach them and how to solve those problems, which I would argue is kind of probably the most fun part as well as the most useful part of organic chemistry. But like I said, this is kind of a huge shortcut for you when your starting point is an alkane. Okay. Of course, keep in mind some of the stuff we've talked about in this chapter when it comes to this. Using bromination is much more regioselective than chlorination, so be careful when you select chlorination. Look at your substrate and see that if there's only one place for a hydrogen abstraction, then chlorination's safe. Otherwise, you might want to do bromination. Okay, and so we can, if you want to avoid polysubstitution, a good example is is to use NBS, right? Remember that only produces one bromine radical. Okay, so that might limit the amount of bromine radicals you have floating around. Okay. All right. Another thing to keep in mind is also temperature. Lower temperatures will prevent the reaction running out of control. Okay. So here's an example with where chlorination is allowed, right? So in addition to limited sites, basically if you have a highly symmetrical site, that kind of limits the type of product you can make. So here we have chlorohexane. All of these hydrogens are essentially equivalent, right? No matter where you substitute a hydrogen for a chlorine, you're going to get chlorocyclohexane, right? It doesn't matter where. Okay. That being said, of course, with chlorination, you've got to be careful with the with polysubstitution too. Okay, so that's something to keep in mind. Okay, but the bottom line is once you have your halogen on your molecule, so you do that first step that gets a halogen on there. Now you have a reactive substrate with a good leaving group that you can do a substitution reaction. Okay, and that can go on to do other reactions that we've seen on the chapter with substitution reactions. You can do, for example, you can do an elimination reaction here, or again, with your leaving group, you can go directly to this elimination reaction, produce an alkene. And now you've got all of those addition reactions we saw in the chapter with alkenes. So you've got lots of synthetic options here. Okay, so keep that in mind, as, like I said, a good tool in your synthetic toolkit. Okay, and again, we'll practice this a lot more in the next chapter. Okay, and that's it for this chapter. So let's walk through some of these practice problems. Okay, so this first one is just an explanation one, so I'm just going to skip to the answer here. Again, like this is, I'll try and focus more on the application type problems, the actual problem solving. Okay, here we go. Here's a good one to practice. So go ahead and take a second, pause this video, and draw all of the significant resonance contributors here. Okay, notice that you're starting off with a radical that's in an allelic position. So my advice is start off by drawing the resonance structure of that, and then when you draw that radical, ask yourself, is that allelic to any other positions, and so on. Okay, so hopefully you've taken a crack at that now. And here are your different radicals. So notice that here you've got an allelic system, right? So if you switch over this double bond, I guess I can draw the arrow pushing so you can see how this works. So basically, if this comes down here and this pi bond opens up so that one electron goes here and one electron goes here. Oops, I guess I could have drawn that the other way, but anyway, so I've curled that arrow in on itself, but that's not important. Anyway, that's why that pi bond forms over here and why we have a radical here. But notice that now we have another allelic system. Okay, so we can again have that electron go like that, and this pi bond split up accordingly here. And that's why we wind up forming a pi bond here and having our radical move over here. So this carbon, and this carbon, right, all have partial radical characters, and all of these carbons here have partial double bond character. And that's why the hybrid looks like that. Okay, please note that the double bond up here is not involved in this conjugated pi system. Okay, so it's not included in that hybrid. It's just left alone. Okay, so here are some some mechanistic steps, and so for each of these, ask yourself, what is wrong with these? Okay, so let's look at each of these in turn. So in this first one, right, what's going on here? Well, it has, if you look at the difference between this molecule and this molecule, what we've done is we've shifted this methyl group over. We've essentially done a rearrangement, but I pointed out back in one of the key differences between carbocations and radicals. While carbocations can do rearrangements, radicals do not. Okay, so this just doesn't happen, right? The ability of this methyl group to react with the radical and shift over like that is just not feasible. Okay, all right. In this step, we have this is a little bit misleading, right? So notice that we've got a double barbed arrow here, right? That implies that this radical is almost doing a nucleophilic substitution. It's like almost doing an SN2 reaction, kicking off the iodine as a leaving group, right? This iodine should be leaving as an iodide with 2 electrons, but we don't see that, right? We only see a radical forming. Also, the other thing to realize is this is just 1 electron going here. 1 electron does not a bond make. You need 2 electrons to form a bond, right? So radical arrows, those fishhook arrows, don't do that. Whenever you want to form a bond with fishhook arrows, you always have 2 of them meeting together. So it's always, so if you had, in your coupling reaction, for example, or addition to a pi bond, if you had a radical here, then you could see these 2 meeting together to form a covalent bond that way. But you would need 2 of these fishhook arrows to provide the 2 electrons for that covalent bond, and that is not the case here. Okay. Over here, this one's a little bit tougher to see. But again, notice that we have those double-headed arrows, right? We don't have those fishhook arrows that you have to consider typical of a radical. This would make sense if this were a carbanion. If we had 2 electrons moving, if this was a pair of electrons and this was a pair of electrons and had a negative charge, this would make a lot more sense, right? You'd form, the pair of electrons would form this covalent bond, and both of these pi electrons would move over here to form a carbanion. But here, this is not happening with a single electron. Again, you want to show this with a fishhook arrow. So if this were a proper, if what you should have had was a fishhook arrow going from this radical into empty space, and then this pi bond cleaving, where this is a fishhook arrow making this radical, and you had another fishhook arrow going out here and forming a bond with that radical. So it would have looked something like this. Oops, I need to go back. Turn the pen on. There we go. So it would have looked something along the lines of this. So here you have your radical. Here's your alkene. So you would have had 1 fishhook going here, 1 fishhook going here, and another fishhook going here. And that would have yielded this product. Okay, so these 2 fishhooks over here are making this covalent bond. Okay. All right. And again, of course, you have a fishhook here, not a double barbed arrow. All right, and then for this last one, here it looks like they're trying to do a hydrogen abstraction. So you've got a again, you've got a single a fishhook, right? A single barbed arrow trying to form a bond. I think that's the key thing where we're going wrong with these. You always need 2 fishhooks to come together if you're forming a covalent bond, because you need 2 electrons for a covalent bond. You can't form a covalent bond with 1 electron, right? So the key thing is that basically the electron from this so basically, I guess what we're missing here is we needed another arrow to come up here and meet this one to form this bond. Okay, so it's not shown, but you have RH as your other molecule that's leaving here. And then of course this 1 electron, 1 electron from this bond forms this radical. Okay, so they got this arrow right. It's just they forgot the second arrow showing that the second electron from this covalent bond goes into forming this bond over here. Okay, so let's look at a bromine substitution here. So have a look at this molecule and predict the major product. So probably look for a good tertiary site for that bromine to add on there. Okay, think about the radical that you would have that bromine react with. Okay, so once that hydrogen's plucked off to make a I'll go ahead and just say that you have a tertiary radical here. Remember the stereochemistry of that tertiary radical. Okay, remember the fact that that bromine can add to either side of it. Now, that being said, keep in mind that we've got a ring compound here, and so you want to consider whether your groups are axial or equatorial. Okay, so the hint there is that bromine is less bulky than a methyl group, so you probably want your methyl group to be equatorial as opposed to your bromine. Okay, it's okay to have an axial bromine if it means not having an axial methyl group, is what that hint is telling you. Okay, so pause this and see if you can figure it out. Okay, so hopefully you've figured out that that carbon all the way on the right was your tertiary site. So you do a hydrogen abstraction there. Of course, your bromine can add to either side of that carbon, right? Because it's a radical, right? So you have a shallow interconversion, and your bromine can add to either side. That being said, you want out of your products, it makes sense that this one's kind of stable, and you can have that methyl group um, at the equatorial position. So even though there's steric strain between the bromine and this methyl group over here, it's okay because it's better than the steric strain between these two methyl groups here. So you may be tempted to also just have the bromine at this equatorial position here, just especially based on the way that the substrate's drawn. You just have that bromine swapped out for that hydrogen here, and that's probably okay. Like the slide here kind of drew both. I'm just telling you that, like, in terms of if you had to choose between these two products, this one over here is definitely the more stable. Okay, so something to keep in mind. All right, so here is another reaction that I want you to try and figure out the answer to. Okay, so notice that here we have, notice this double bond is making this a little bit different than the previous reagent we had. Okay, I think hopefully you guys, if you think about it for a second, why do we use NBS instead of bromine? Okay, and the key answer to that is that alkene over there, right? Remember, bromine will do an addition reaction across that alkene. So using NBS prevents forming that addition product, competing for the product that you want. Okay, so feel free to pause this and ask yourself, what is the product you get with just a bromine radical substitution using NBS? Okay, so with that alkene, you have to keep in mind that we have some allelic positions that can tack on that bromine, right? Not over here on the left, right? Because there's no hydrogen to abstract there, so that's not going to form. But we have an allelic position over on this carbon up here, and we have an allelic position on this carbon down here. Okay, now out of those two positions, this one's probably preferred because it's a secondary site as opposed to this primary site. Okay, so you're going to form a secondary radical that is allelically, that's in the allelic position. Okay, now you also probably want to consider the resonance structures that would form accordingly. Okay, so of course, if you just have the bromine add-on here, that's one product. The resonance structure will yield this product over here, right? So this double bond swings over here and makes this carbon allelic, your radical. And so that's why the bromine adds here for the other major product. Okay. The same products can form as well. Again, because your bromine can attack either side of that radical. So you can have this bromine come in equatorially or axially. And of course, you'd prefer that large bulky bromine to be equatorial, right? So that's why this is considered the major product, and this is a minor product. Okay, and as I pointed out, this is going to be a minor product as well, due to the this being a primary site. So even though it's allelically stabilized, that's still going to be, that's not going to have as large a percentage as these products. Also, keep in mind the allelic stabilization with this radical has a resonance structure where your double bond, well, I guess your double bond would move over here, so they haven't really shown that. I guess that's another product that could form. You could have a bromine over here, so it would look kind of like this product over here, except instead of the double bond being here, the double bond would be up here. Okay. Granted, that has a less substituted alkene, so that's probably why that's another minor product. Okay, let's try a radical polymerization reaction. So here's a polymer, right? So ask yourself, what does the monomer for this look like? Okay, so remember, your monomer always has a double bond, where the double bond opens up to give you the links to the next monomer in the chain. So each of these bonds that are shown here, going through the brackets of our polymer, would be removed, and instead you would have a double bond between those two carbons. Okay, so basically it looks like that. That's your monomer. Okay, and that's it for this chapter. So be sure to try out some of the homework problems. As always, if you have any questions, let me know. Check your work with the study guide. And yeah, good luck.